When we were introducing the inner product, I mentioned that a row vector sits next to a column vector. We write x transpose y, and the resulting thing becomes a scalar. We did not discuss what this scalar would be yet. We will understand what we get when we do the inner product of two vectors sitting next to each other, particularly with x transpose y way. And I used my pens to show you that the inner product to happen, a column vector and a row vector x transpose y should look like this. Well, in order product, if a row vector sits at the other side of the column vector, meaning when you get xy transpose, we call this operation an order product. So remembering from the inner product, we mentioned that when a column row vector sits next to a column vector, we get one scalar. Everything gets mushed into one scalar. In order product, we are talking about something else. In order product, what we have is this time a column vector sits next to a row vector. So xy transpose gives you a z. So this xy transpose looks actually like this. So we are talking about a column vector and a y vector sitting next to it, and the resulting thing is a matrix. Unlike the inner product, this operation is actually operation does not simplify from two vectors to one scalar. It takes two vectors and then gives you a matrix. In this operation, every single element of the corresponding row and the column gets multiplied and populates the corresponding index of the resulting matrix. So what we are talking about is actually a matrix multiplication. If you remember the matrix multiplication, when we are populating the output, the first row, first column element of the resulting matrix, we are taking the first row of the first matrix. Let's see this as a matrix, and this is also a matrix. You can see this as a matrix too. First row of this one and first column of this one, get the inner product. Well, inner product of two scalars is just their multiplication, and place it here. And first row, second column, it comes here. First row, third column, it goes here. So what we're talking here is that when we calculate the order product of two vectors, every single element multiplications happen. And therefore, when we start with an n by 1 matrix, just by 1 because it looks like a vector, but it's actually an n by 1 matrix, and we are still keeping the inside dimensions match 1 by k, another matrix, which is a row vector, but it's a matrix. We are resulting in an n by k resulting matrix, effectively canceling out this inside dimension. Just like the matrix multiplication, this time instead of doing the inner product of the corresponding inside dimensions, we're just doing the scalar multiplication. Before I finish, I would like to mention two things. One, you see that if this is a vector, if this is a matrix, and I'm multiplying every single column, multiplying with every single column of this other vector, so you can see that the columns of the resulting matrix are just multiple of the input column. So the first column of the Z, capital Z, this matrix, can you see that the first column Z11, Z21, all the way to Zm1 is nothing but y1, which is a scalar, times this whole x. And the second column is y2 times whole x. Similarly, you can see that the rows of the resulting matrix is this row vector scaled with each and every one of the row scalar of the first matrix, first column vector. And therefore, we will have rows that is going to look like each other, except they are scaled with a different vector, the different scalar. So there is a name for such matrices. Even though this matrix has size n by k, and you might think that it can have m times k different numbers, you can see that they're actually not so different. This matrix has a kind of harmony. It has a harmony that the columns are scalar multiples of each other, and the rows are like this. So there is not so much information hidden there. The only information, the interesting information, since all of the rows resemble the row that manufactured it, so to say, the rows are coming from this row. And columns, similarly, resemble the one that is making it. So when we think that this matrix has so much different information, m times k different scalar values, but actually not. There are the information that's hidden there is not so rich. And very soon we will introduce the concept of a rank. So the rank of this matrix will be only 1, because there will be only one column that populated this. Everything is everything is a replica, not a replica, but a scaled replica of it. And similarly, the rows are very similar to each other. There's not much new information there. So that's the first thing that I wanted to talk about this matrix. And the second thing is how you are going to see this matrix. This matrix, we mentioned that in deep neural networks, matrices are tunable parameters that takes vector as input and yield another vector as output, which is to be used by the next weight matrix, right? Turns out the direction or the update to change these weights is actually an outer product of the input that it was fed with and the error that this input created. So when you take the input of a matrix, whatever the input was inputted during that training point, and the transpose of the error with respect to transpose of the gradient of the error that this input generated. What error? Error is the difference from what we think that the neural network should emit and what it actually emits. And you take the outer product to get your update. But we are too early in our journey to discuss this, but just a heads up that you will see this operation soon when you get to the updates of the matrices in neural networks.